optimizing cloud task scheduling in Cloud VMs with accurate vCPU abstraction, which was conducted under the advisement of Dr. Jianchen Shan from Hofstra University and in collaboration with Dr. Weiwei from the University of Rhode Island and Dr. Xiaoning from NJIT. There is a problem with systems and virtual machines, in that virtual resources are not hardware resources, and guests do not have accurate access to the underlying provisioned resource information. Systems that rely on accurate resource information and that were originally built for strictly hardware resources are currently insufficient to deal with virtualization, leading to many problems. In our work, we focus on improving the task scheduler's ability to deal with these problems in virtualized environments. In order to quickly introduce vCPU abstraction, I will first present a pretty simple example of two processes time sharing on a single physical core. Process 1 runs from time step 0 to time step 2, and process 2 runs from time step 3 to time step 5. As the CPU can only run one process at a time, process 2 is inactive when process 1 is active, and vice versa. Now, a vCPU is a process thread created by the hypervisor to handle simulation of the guest OS CPU. Whenever a task is being run on a guest core, it is being run on the host in the corresponding vCPU. Since vCPUs are processes, they are movable and interruptible. The time a vCPU spent interrupted, in the case for vCPU 1 time 3 to time 5, is called steal time. During steal time, a vCPU is unable to run any tasks. The percentage amount that a vCPU is available to run is called its capacity. In this example, both cores have a capacity of 50% due to only being able to run half the time. Capacity is calculated using time stolen from the core, but there are problems with how we measure and how we consider capacity. Chiefly, idle vCPUs have no time to steal and are mistakenly assumed to be at 100% capacity always. In this example, we can see that capacity is being measured dynamically until the core is idle. When the core is idle, we have no information on its capacity. Now it's assumed to be at 100%, yet a task might still be stolen from if it begins to run on the vCPU. Here's an example of this incorrect capacity assumption misleading the scheduler and causing performance degradation. Here we have one task being run and two vCPUs. vCPU 1 is able to run tasks 66% of the time, so its true capacity is 66%. vCPU 2's true capacity is 33%. Once our task starts running on vCPU 1, we have an idea on its capacity. Because vCPU 2 is idle, it's assumed to be at max capacity. To the scheduler, the choice is obvious. Between 66% and 100%, the task will be chosen to be moved to vCPU 2. Yet we know vCPU 2's true capacity is 33%, so the task is only able to run for 33% of the time. Now vCPU 1 is idle, it's assumed to be at 100%, and the task scheduler again makes the obvious decision to move it back to vCPU 1. We can see what happens is that the task continuously swaps between these two vCPUs, and ends up using much less CPU time than it would have, simply staying on vCPU 1. This is due to the poor scheduling decisions based on inaccurate capacity, where a task is moved from a stronger vCPU to a weaker vCPU. An additional problem is the lack of consideration of vCPU latency. Capacity is not the only metric that matters. Two vCPUs could be identical in their capacity, yet have varying effects on tail latency. You can see in this example that both of these cores are active for half the time, but the way they are active is fundamentally different. A task starting on time step 3 on the high latency vCPU has a much longer time to wait before the vCPU becomes active again, as opposed to the low latency vCPU, where the vCPU is only inactive for a single time step. Another consequence of the unique properties of vCPUs is something we like to call the running task problem. This happens when a running job is stalled, even when there exist idle vCPUs that could run the job. You could think of it in broad terms as time available versus time used. In this example, there is a VM running one task with 3 vCPUs where each vCPU has 50% capacity. There's 150% available CPU time between all 3 of these vCPUs. Yet if you were to run a task in a standard way on one vCPU, the task would only be able to run 50% of the time, even though there's 150% time available. Ideally, the task can rotate between each core, harvesting the CPU time available to it, and migrating before the vCPU becomes preempted. This would allow the task to run nearly all the time. vCPUs are not only interruptible, they are also movable. This means that vCPU topology can change dynamically when the host moves vCPUs. These changes are unknown to the guest VM, and can interfere with standard topology-based scheduling. In this example, our guest VM has 4 vCPUs and is initially correct about their topological layout. The guest then schedules task 1 and task 2 as far apart as possible to allow each task to get access to the most die space into vCPU 1 and vCPU 3. Yet the host, for a variety of reasons, can choose to move the vCPUs. The guest is unaware of what's happening and is now failing in its objective to maximize die space for each task, since task 1 and task 2 are on the same core. Here's one more example of a very unique problem caused by the properties of vCPUs. When 2 vCPUs from the same VM are assigned to the same core, a low priority task on one can interfere with a high priority task on another. In this example, we can see that from the VM's perspective, everything is as normal. The VM schedules a high priority task onto vCPU 1, and seeing vCPU 2 is empty, schedules a low priority task there. But on the host, the vCPUs themselves are scheduled onto the same CPU, and the host timeshares between the vCPUs, so the host controls how these 2 tasks are scheduled on the CPU. Yet the host lacks the knowledge that one vCPU contains a high priority task and one vCPU contains a low priority task. To the host, there are just 2 vCPUs and are treated equally. This leads to priority inversion, where a low priority task interferes with a high priority task. If you were to schedule both tasks onto the same vCPU, vCPU 1 in this case, the guests would take control of the scheduling and be able to run the high priority task over the low priority task consistently, removing the priority inversion problem. So we've identified some significant challenges with current virtual machine scheduling, and several notable approaches have already been proposed to address the issue. First, CPS improves scheduling by having the hypervisor share CPU load and topology information with guest VMs. Similarly, XPV exposes NUMA topology details from the hypervisor to the guest VM. ECS has the guest VM provide hints to enable the hypervisor to prioritize vCPUs running critical section tasks. UFO shares scheduling frequency information from the VM to improve host core allocation. One important characteristic these solutions share is that they rely on paravirtualization. This means they require modifications to the hypervisor and necessitate communication between the host and the guest VM. Unfortunately, this reliance on paravirtualization introduces several limitations. 1, it creates compatibility issues, making these solutions difficult to apply universally, especially in the diverse ecosystem of multi-cloud environments where closed-source hypervisors are present. Integrating multiple solutions is challenging, particularly when each has distinct and sometimes conflicting scheduling goals. For instance, ECS aims to prioritize critical tasks, while UFO chiefly aims to reduce latency. Furthermore, paravirtualization expands the attack surface due to increased communication between host and the guest, raising security concerns. Another limitation is the inherent assumption that all VMs on a hypervisor share similar scheduling goals. In practice, different VMs often have different scheduling needs, some prioritizing throughput and others latency. Existing solutions apply uniformly, which makes optimizing for these individual VM goals difficult. Given these challenges, we pose the following question. Is it possible to create a comprehensive, non-paravirtualized solution that enables each VM to independently achieve its own scheduling goals? It is, and we achieve it with the vSCHED approach, in which our goal and our main challenge is to have a solution that functions without any support from the hypervisor. We probe, we deduce, and then we benefit. First, our probers tell us key information about the system and then deduce the correct abstractions. Our topology prober uses cache line transfer latency to probe for distance between pairs of cores, and through these pairs can deduce a topological mapping. Our capacity prober periodically initiates a sched idle workload and gains an accurate view of a vCPU's capacity. And we can probe for latency by measuring how the stolen time is distributed. We benefit in part by feeding all of these correct abstractions to the current scheduler, so it can make correct decisions, but we also benefit from leveraging our 3 new heuristics that are designed specifically for virtualized environments. Here's an example of our topology prober tool, vTopology, in action. First, we measure the latency between vCPU 1 and vCPU 2. I think the animation isn't, sorry. Since the time frame is rather short, information between these vCPUs is transmitted rather quickly. Thus, we can determine that they are in close proximity. Because we know they're in close proximity, we can also glean some topological information. We know they are in the same core, and thus in the same NUMA node. Now we can introduce a third vCPU and test its latency with vCPU 2. Okay. We get slower data transfer, and thus we know that the vCPUs must be farther apart. With this, we know more information. vCPU 3 is in a separate NUMA node, and thus it is in a separate core from vCPU 2. Note that we do not have to test between vCPU 1 and vCPU 3, as we can deduce their relation from previous tests. And this is how we are able to probe for and deduce a full topological mapping. Guests are blind when a vCPU is idle. Our solution is to have probers periodically start a sched idle task and measure how time is stolen during its runtime. Using this stolen time, we calculate the capacity using an exponential moving average to smooth out measurements and prevent unnecessary migrations. This approach lets us have up-to-date, accurate knowledge of capacity, even when a vCPU is idle, and allows existing tasks to be affected minimally. Additionally, because we can also measure the amount of times that a vCPU is preempted, we can deduce the average latency using the stolen time and preemptions. For example, the first and second period here have the same capacity, but differing latencies measured through preemptions. Here are some results on how our probing improves the scheduler. We test vCapacity in a VM with 4 vCPUs that have higher capacity than the rest, and we can see that vCapacity allows tasks to spend more time on the strong vCPUs, leading to an increase in throughput. We test vTop by running 16 threads in a VM with 32 vCPUs pinned onto 16 physical cores. vTopology allows the scheduler to utilize more cores by avoiding idle vCPUs with busy SMT siblings. Not only can we feed all this information to the existing scheduler to improve performance, but we can develop new heuristics. The first is biased vCPU scheduling, where we correct the lack of consideration of vCPU latency. We first use PELT to determine if a task is latency sensitive, and if it is, we use BVS to allow for vCPU latency to be considered in its core selection process. This is a simplified version of the system. For more details are contained in the paper. Now we are able to put the task on the core with much lower latency, leading to shorter inactive periods and a much shorter response time. The current scheduler is work conserving, meaning that an idle vCPU should always be used if there are runnable tasks. Yet this is not always correct in virtualized systems. 2 vCPUs could be stacking on the same physical core, in which case the best option is to simply never use vCPU 2 and allow vCPU 1 to use the entire core uncontested. The guest loses no CPU time and gains the ability to avoid problems, like priority inversion, and vCPU exits when the host swaps between the 2 vCPUs. Also, if a vCPU becomes contested enough on a CPU, it could become a straggler vCPU. If a vCPU has, say, only 5% capacity, it is unlikely to contribute significantly to process runtime and introduces the severe risk of a critical section task being greatly delayed by it. Such vCPUs are not worth considering. We can detect stacking cores with vTopology and straggler cores with vCapacity, and we can use C groups to remove them from scheduling consideration, relaxing the work conservation invariant. Before, we addressed that an ideal solution to the running task problem, where 150% CPU time is available and only 50% is used, is to simply move the task constantly to harvest the available time in the system. However, naively moving is not enough. There are many complex considerations in this preemptive harvesting movement. One of them is the wake-up latency of a vCPU. When a task is migrated to a previously idle vCPU, the vCPU itself needs some time to wake up, and the task cannot run during this time. This eats away at the potential gains. We have developed something we call activity-aware migration to avoid the overhead of this wake-up latency. Here's an example of the process. This task runs from some time on vCPU 0 before initializing migration and signaling vCPU 1 to wake up. The task stays on vCPU 0 and runs as usual until vCPU 1 does wake up, then vCPU 1 starts a stopper thread on vCPU 0. The stopper thread then migrates the workload to vCPU 1, which is currently active, and the task is able to start running immediately. This way, we can mitigate the impact of the wake-up latency, this time between T2 to T4 on vCPU 1. There are times when such a migration is not desirable, like when one of the vCPUs becomes preempted. In these cases, we can simply cancel the migration and have the task stay on the core. Here we have some results from vSCHED on two commonly used distinct types of VMs undergoing contention. We can see here that during this time, vSCHED is able to significantly improve throughput and latency. Each VM has varying latency and capacity across its vCPUs. A more detailed description of the evaluation in our VMs is in the paper. We can also see that we are able to do this with low overhead. The negative overhead that you see for some workloads is because the sched idle tasks keep the cores warm when they otherwise would have been idle. To conclude, we have shown that the task scheduler and guest virtual machines can be extended with vSCHED to improve workload latency and throughput with low overhead and respond to the vCPU dynamics. vSCHED's primary target is in multi-tenant and multi-cloud environments and for contested VMs. vSCHED is less applicable to dedicated bare metal server VMs where there is no contention. vSCHED is also orthogonal to existing solutions, and many components of vSCHED can work alongside hypervisor level optimizations. We can fill observability gaps when information cannot be passed from the hypervisor to the guest or from the guest to the hypervisor. vSCHED is also open source. You can check us out today. vSCHED has many potential applications. IVH can be used to prioritize lock holding tasks and harvest the lock waiters. vSCHED can be extended to improve other mismatches in vCPU abstraction, like energy states used by EAS, and the vSCHED approach itself can be used to address other virtualized resources with inaccurate abstractions, like memory. Thank you for listening. Any questions?